Well, welcome back, everybody. And give me a second and let some more people in. Okay. All right. I hope everyone had a good weekend. We will continue here. The semester's going pretty fast. All right. Let me share the I've got more people coming in. Uh-oh. One second. Okay. Our calendar, just to make sure that everybody's is aware of what's coming up and where we're at. Today is the 16th. We will complete chapter 5 and then can jump into chapter 6, which is a pretty short chapter. A lot of the stuff in chapter 6 I've already introduced is about the periodic table. I did move activity 5 and homework 5 to Thursday, give you a little more time to work on that. And then on the 20th is activity 6, and then next Tuesday will be exam number 2, which you cover chapters 4 through 6. The videos you sent me, I should be done with all those by the end of the day, if not tomorrow for sure. I'll go back, I'll send you back comments and so forth. So far, they look pretty good as far as the isotope activity. All right. Any questions? Okay. All right. Well, tell you what, let me start off with where we ended up. We were in chapter 5. Slide number 39, which puts us right here. Okay. I will back it up. One we were talking about the elements and what happens to the elements with respect to losing or gaining electrons. And this concept sometimes gets a little bit difficult to understand, but think about this whole thing of making ions, okay? Because, we all stated earlier, 118 elements, okay? They have an equal number of protons, equal number of electrons. Think of as we know, the protons have a positive charge. The electrons have a negative charge. And so if I have one positive, one negative, my overall charge is a 0. Now I call it charge, but later on we're going to change that name to oxidation number. Right now, the charge of all the elements is 0, okay? The charge of all the elements is 0 because they have each one of them has an equal number of positive protons and equal number of negative protons. Now, when the elements lose electrons, okay, they lose negativity, they lose electrons, and then the net now becomes positive. Now, for example, sodium has 11 protons and 11 electrons as an element. It's a metal, and like I stated, all metals want to lose electrons, and so it's going to lose 1 electron. And the reason it's going to lose 1 electron is because on the periodic table, it is in group 1A, which tells you that it has 1 of those 11 electrons. One of them is on the outermost shell or the valence shell, which is in period number 3, okay? Energy level number 3. Now, rather than having to fill up that outermost layer 7 with more electrons, which energetically is unfavorable, it's much easier to lose that electron because now by losing 1 electron, now you have positive 11 neutrons and protons, and not neutrons, protons, which is 11 and 10 electrons, which is negative. So I got 11 positives, 10 negatives, which gives me an overall net of a +1. That is the ion, okay? Because it lost that 1 valence electron, the outermost shell, which was in the 3rd energy level, now its valence shell is number 2, which happens to be full now, it has obtained the octet rule. It has attained those 8 electrons around the outermost shell by becoming an ion. The converse of that are the nonmetals that are close to the noble gases. They want to gain electrons. Nonmetals gain electrons because that fills up the outermost shell to that magical 8, the octet. And so fluorine, for example, has 9 protons and 9 electrons. And of those 9 electrons, 7 of them are in the outermost shell. It just needs one more to fulfill the octet rule. Therefore, it rather pick up 1 electron than lose the 7 in the valence shell from an energy perspective. And by picking up the 1 electron, now it has 8 electrons around the outermost shell. Now it has 9 protons and 10 electrons, giving you a negative net overall charge. Okay. All right. And so you can use the periodic table to help you determine what kind of charge they will have, because from groups 1A to 2A and 3A for the metals, because we're in the metal domain here, with the exception of hydrogen, which is in a group 1, but it's not a non-metal. Okay, being a metal, they will lose electrons in their respective charge. Would be +1, +2, and +3. Now, some people have asked me, does it make a difference whether I write it 2+ or +2? No, it does not. Okay, it's the same thing. Like here in the example, magnesium +2 versus magnesium 2+. It is the same thing. It is understood that a plus means there's a 1. It's not necessary to put a 1 in front of the plus or after the plus. You can just put this plus symbol and that will suffice. But if you feel more comfortable, that's not, you wouldn't be incorrect to include the value 1. You'd be at +1 or -1. Okay. Excuse me. So group 7, like I mentioned, group 6, these guys, and group 5, these nonmetals will gain electrons. And by gaining electrons from 5A to 6A to 7A groups, they had the corresponding charge of -3, -2, and -1 after they gain the electrons. Okay. Now, once they gain electrons, they have a new name. They are called anions. So an anion is an element that has gained electrons and has a negative charge. Up to this point, we've been saying just ions, and ions is a very generic term, encompasses both positive and negatives. But now we're becoming more specific. So an anion is an element that has gained electrons, which, because it gained electrons, tells you it's a nonmetal. Okay, like I stated, nonmetals gain electrons. So group 7A, 6A, and 5A all have a overall -3, -2, -1 respective charge because they gain an electron. Okay. As I stated, metals want to lose electrons and they become, their new name is cations. Okay, so there's a difference here. Cations and anions. Those are the specific names for ions. So metals that lose electrons are called cations. Nonmetals that gain electrons are called anions. Okay. Sometimes it helps to remember the name. Okay, to me, if you look at the N in anions, meaning negative, that may help you remember who's who. Okay, for some reason, I don't know why, but I think cat is positive for cations. It just doesn't make sense, but that's how I remember it just when I first started. Okay, so whatever works for you to help you remember what's what. Okay, so what about group 4? Well, group 4 is very special, okay, because let me explain why it's very special. Let me share it. Group 4, which would be these folks right here, group 4A, because they have 4 valence electrons. Okay, 4 valence electrons, all of them. Carbon number 6 has 4 valence electrons. Silicon number 14, 4 valence electrons. Now, by virtue of the fact of having 4 electrons and looking at the magical 8, if you will, okay, the stable 8, it's half of 4. So what that means is for the folks in Group A, for the elements in Group 4A, they have the capability of either losing all 4 electrons or gaining 4 electrons. From the energy perspective, it's about the same. It is. I mean, we either gain 4 or lose 4. It's going to be the same. Now, how it happens depends on the reaction conditions. Okay, and so sometimes they lose 4. Sometimes they may lose a whole range actually from -4 to +4. So Group 4 guys are very special. They can have a charge of +4 all the way down to a negative charge, meaning I'm going to lose all 4 or gain 4 or any combination of 1 or 2 or 3 or 4. Yeah, that kind of scenario. And it's pretty slick too, because what you're also hopefully picking up is this, that on the periodic table, depending on the group that they're in, also tells you the number of bonds. So we're going to be talking about bonds here in the next couple of chapters, and how these elements come together to form an actual bond. And there what you can use as a guideline is the group that they're in. For example, the folks in Group 5A, okay, the nonmetals, nitrogen and phosphorus, they gain 3 electrons, okay, having a total overall -3 charge. But what that also tells you is when they actually make compounds, the maximum number of bonds they can make is 3. It kind of helps you out. For example, ammonia, NH3, there's 3 hydrogens bonded in the central atom. Group 6A, these elements by themselves, the nonmetals, will gain electrons having an overall -2 charge. What that -2 also tells you, or that 2 tells you that when these elements form bonds to make compounds, the maximum number of bonds they can make is 2. For example, oxygen, hydrogen, H2O, good old fashioned water. There's 2 hydrogens per 1 oxygen. Hey, that's 2 bonds. We'll learn more about the bonds in a bit, but this is just a little additional assistance to help you out to figure out, hey, does this structure look right? Well, let's find out where it's at on the periodic table. Now, if we look at the nonmetals in Group 7, all of those guys have 7 valence electrons, and they will gain 1 electron. Okay, so having a negative charge. Okay, which means the octet is full. Well, that -1 charge, that 1 also tells you that when these elements form a bond, the most number of bonds they can make is 1. For example, HF. HF is hydrofluoric acid. Okay, 1 bond, 1 hydrogen. All right. So the position in their periodic table will tell you the relative size of each element. It will tell you how many valence electrons you have for the 1A through 8A, the 8A elements. We're going to learn more about everything I've been talking about is called periodicity. Its position in its periodic table gives you a lot of information with respect to the type of molecule it is, the type of element it is, how many bonds it can make, how many electrons it can lose or gain, okay, so on and so forth. All right, so that's why I tell you that I refer to the periodic table quite a bit. So let's go back to that and finish it up. And Group 8A, of course, they are the noble gases, what we call noble gases, and therefore, because the valence electrons there are full with 8, that's it. They cannot make any more. Why? Because from an energy perspective, it's just not energetically favorable. to add electrons from a noble gas means I have to put them in the next higher valence electron or energy level, which from an energy perspective is not very favorable. Can it happen? Sure, but can it stay there? No, because again, it's not very stable position. All right, and to remove electrons, we're going to learn here a property called ionization energy, and we'll learn that the noble gases, because they have 8 and they have a lot of protons, they hold on to their electrons very tightly. So to remove one is pretty tough. All right. So going across the board from the far left, only speaking about the A elements, we go from a +1, +2, +3 to group 4, which can have a plus or a -4, and then group 5, -3, -2, -1, and then a 0 charge. Those are the corresponding charges / oxidation numbers that those elements in that group can have. Okay, so how do we determine, for example, what charge will they become when the element is just given? When the name of the element is just given, then we use the periodic table to say, okay, is this thing going to have a negative or a positive charge? And then if that's the case, is it going to, what is the magnitude of the charge? All right, so let's take a look at the first one. Well, to do that, first thing we do is use your periodic table. Find it. Where is it at? Okay, lithium is element number 3. Okay. Let me, oh yeah, right here. Element number 3 right there. Okay. So once we determine where it's at, and we determine, okay, is it a metal or a non-metal? Well, obviously being in the far left of that stair step, you see that stair step on the far right? Being in the far left there tells you that it is a metal. Now, being a metal tells you the second part. It's going to lose electrons. So the next part is, well, okay, it's going to lose electrons. I'm going to have a positive charge. Well, how many electrons it's going to lose? Well, then we determine that it is in group 5, the 1A, which tells you you have 1 valence electron. And so that tells you the magnitude of the charge it's going to have. So one, we have, if we determine it's a metal, we determine what group it's in, which tells us how many valence electrons it's going to lose, which tells us the charge. Okay, so we go back to the question. So lithium would have, when it becomes an ion, a +1 charge. Okay. Magnesium, similar scenario. Take a systematic approach at each one until at such point in time you become comfortable with it. Magnesium, point 1, it's a metal. Okay. Second point, determine where group it's in. It's a 2A element, which tells you I got 2 valence electrons. It's a metal, it's going to lose those 2 valence electrons, which tells you the charge, which would be a +2. Okay. All right, the next one, sulfur. Find sulfur in the periodic table. Okay, let's do that. Let's bring up the periodic table, look for sulfur. We'll see here that sulfur is number 16 right there. I've highlighted in yellow. It is, so we found that in the periodic table. From there, determine whether it's a metal or a non-metal. It is a non-metal, is to the right of that stair step. It is a non-metal, which then tells you that if it's when it becomes an ion, it would gain electrons. Okay, gain electrons. Now, next question, well, how many would it gain? Well, we find it in group 6. It's in group 6, which tells you there's 6 valence electrons, which tells you furthermore that you need 2 electrons to fulfill the magical 8, okay, which is the stable state to find the octet. So therefore, it would have a -2 charge. Let me rehash all that so you can go through a systematic approach. To find the element on the product table, sulfur, okay? Mark it for me. I mark it so I know where it's at. Next thing I determine, is it a metal or a non-metal? To determine that, I look at the stair step, okay? it is to the right of the stair step, which tells me it's a nonmetal. Now that I understand it's a nonmetal, that tells me it's going to gain electrons, not lose them, but gain electrons. Remember the cardinal rule about losing and gaining electrons. All metals lose electrons, all nonmetals gain electrons. So we know it's going to gain electrons, which gives it a negative charge by picking up electrons. Okay, electrons are negative charge. The final thing is, well, how many? What's the magnitude? We determine that by finding it on what group it's in. It's in group 6A. Being in group 6A tells you I need 2 electrons to get 8, the valence 8. So it would have a negative 2 charge. For sulfur. And the other aspect about that is, we'll come back to the naming here in a minute. Notice that when I talked about lithium and magnesium, I said I just kept the name lithium and magnesium. I just say lithium ion or magnesium ion. Prior to that, it is the lithium atom or the lithium element. Okay. With the sulfur, we change the name to sulfide, but we'll come back to that. All right, bromine. Bromine's the next one. Okay, so we pull up the periodic table, find it on the periodic table. Okay, and find it right here, number 35. It's highlighted in yellow. Okay, so we found it. It is to the right of the stair step, which tells me it's a nonmetal, which tells me it will gain electrons, and the magnitude of that charge is determined by the group that it's in. It is in group 7A, which tells you that it needs 1 electron to get to the 8, the octet. Therefore, bromine will gain 1 electron and have a negative 1 charge. Okay. All right. Nitrogen. Same scenario. And now we'll continue with showing you here. Let me highlight it. So here's nitrogen. Element number 7. It is to the right of the stair step, which tells you it is a nonmetal, which tells you that it will gain electrons. We find the group that it's in, and it is in group 5A, Roman numeral 5A. Okay. And that tells you that I got 5 valence electrons, which tells you, okay, when it becomes an ion, it's going to pick up 3 electrons. So therefore, it will have a negative 3 charge. And certainly it has nitrogen, negative 3 charge. Aluminum, if you go find it in the periodic table, it's element number 13. It is a metal, okay? And therefore will lose electrons. It is in group 3A, which tells you there's 3 valence electrons. The fact that it's a metal tells you that I'm going to lose those 3 electrons, which results in a positive 3 charge. Okay. Now, when these elements start losing and gaining electrons to become ions, as I mentioned earlier, with the metals, we keep the name. So lithium element becomes a lithium ion. Okay. And that's true for all the metals. Magnesium metal or element becomes the magnesium ion. Aluminum becomes the aluminum ion. That's how we distinguish between the element and the ion. With respect to the nonmetals, there's a complete name change. Sulfur now becomes sulfide. So we get rid of the UR in the name and add IDE. Bromine, its name becomes bromide. Okay. So we get rid of the INE and add the IDE. Nitrogen, its new name now becomes nitride. Okay. So sulfur, the same thing. If you look at the group of sulfur, oxygen is underneath the same group. So oxygen, when it becomes a -2, become oxide. Nitrogen, underneath nitrogen, you have phosphorus. That becomes phosphide, same, very similar. The IDE tells you that it is the ion, specifically just the element. Now, not to be confused, notice this is sulfide, SULFIDE. Down the road, when we start talking about what are called polyatomic ions, we kind of introduced them a little bit, but on the far left here, on the far left, you can see like SO4, SO4 -2, SO3 -2. We have sulfate and sulfite, okay, which is totally different than the IDE sulfide. The sulfate, which I've highlighted, ATE, and the ITE, these are polyatomic ion. That means that they're sulfur bonded with oxygen. The IDE, it's sulfide, simply means sulfur all by itself. Okay. Notice the nitrogens has very similar. You got the nitrate and the nitrite, not to be confused with the nitrite IDE of what we just did here. Okay. All right. So cations, the name stays. We just add ion to it. Anions, we completely change the name. Why is that important? Because we're going to be talking about when we get to a chapter called nomenclature. Nomenclature is naming these compounds, writing names for these compounds, and from the name be able to write the formula. So you can see here that what we're doing at this point is we started out talking about the elements and describing about the elements, what they're made up of. Okay. And then we talked about them right now in the periodic table and talked about the electrons and how they're put together and where they're at within the element, and how metals tend to lose electrons and non-metals gain electrons to form these ions. Now we're going to start, not right now, but the next, not this chapter, the next chapter after this, we're going to start putting these ions together to make compounds. In fact, right now, you have probably a couple of hundred compounds that you can put together. Now you're saying, well, how's that? How can I do that? Well, when we put compounds together, keep this in mind. We put positive ions together with negative ions. We put the cations with the anions to make a compound. You put something on your French fries already, right? You put salt. We know it's salt, but I want you to remember when we use the term salt, it is a lot more than just sodium chloride. Okay, we're going to learn that. Salt in chemistry encompasses millions of different compounds and different types. All right, so how does that come into play? Well, we can do this. If I take lithium ion, okay, and I take the bromide ion, I got the cation, I'm going to put it together with the anion. Now, the lithium has a positive one, the bromide has a negative one. The thing to remember is when we put them together to make a compound, we have to put enough positives together with enough negatives together to cancel each other out. So I got one lithium, one bromide. Okay. Guess what its formula is? I can simply write LiBr. And its name is lithium bromide. You just made a compound. Lithium bromide. Okay. Let me change the color here. Let's take one magnesium. Oh. Let's take magnesium and the sulfide. Okay. Now notice magnesium ion cation has a +2, and the sulfide ion has a -2. So I can simply put those two together because the +2 of the magnesium ion is cancels out by the -2 of the sulfide. So its formula would simply be one magnesium that I can write together like that. And I got magnesium sulfide. Okay. Now I use magnesium, but think of all the elements in group 2. You got beryllium, you got calcium, strontium. You can do the same thing with everything. So you can have calcium sulfide, you can have beryllium sulfide, strontium sulfide, and just goes on. The same is true for group 1, where we put lithium bromide. It could be sodium bromide, potassium bromide, cesium bromide, etc., etc. Okay. Now, when we start putting together something different, let's say, for example, let me clear this up a little bit. And I want to put a lithium anion with the nitride. Okay. Now, the lithium ion, the cation, has a +1 charge. The nitride has a +3 charge. So what that tells me is this. So what I do is I write it down. It says, okay, I'm going to need 3 lithiums and just 1 nitride. That's a superscript there. Okay. I'm going to need 3 lithium positives for every 1 lithium -3. And so now that 3 I put in front of the lithium becomes a subscript. So the formula is, and I don't have subscript, so that 3 is a subscript. So it's Li subscript 3 N. And that its name will be lithium nitride. Okay. And again, I emphasize that 3 after the lithium, Li, is a subscript. And that means just like H2O, I got I'd say H2 subscript 2. That means that there are 2 hydrogens per oxygen. Here, this means there are 3 lithiums per 1 nitride ion put together. And that is the formula for the compound, lithium nitride. And so we have, you have probably, I said 200, but probably more along the lines of 500 when you encompass all the other anions, the nitride, the phosphide, the oxide, the sulfide, all the halogens, the chloride, the bromide, the chloride, iodide, so on and so forth. And you just do a mix and match and put everything together with the right number of protons. You have created a large number of compounds. Now, remember, on the periodic table, on the course website, we have a study mate. Remember, I talked about the study mate? In the study mate, when you click that, it will, what happened? Okay, there it is. I had to make it available. I thought I had that. But I can do flashcards, and in there's 140 some different compounds. So for example, I got chromium sulfide, which is the name, and then if I flip it, that gives me the formula. Now again, it doesn't allow subscripts, so the formula for chromium sulfide is Cr and then S subscript 3, okay, and so forth. Here's boron tribromide, okay, there's a formula, and so on and so forth. So yes, that flashcard does help you with respect to help you learn about nomenclature and naming the compounds. And we're just beginning to do that right now. All right.
Are those flashcards on Canvas?
Yes. On if you look at the far left, it's called Study Mate. So click on that, and I just activated. I thought I had it activated, but then you can make it's like 140 some combination of compounds, where you can practice learning the naming of compounds and or the formula. You can also make like a crossword puzzle and some
Okay.
some other things. But the flashcards are pretty helpful. Keep in mind it doesn't support subscript, so that number is a subscript that you see after an element. Okay.
Okay.
All right. So isoelectronic, the driving force here has been is to become isoelectronic, which means I want to have the same number of electrons as the closest noble gas. Okay. It's important. I'm not becoming the noble gas. We are having the same number of electrons only. Okay. So group 7 element or anions have gained 1 electron. So now they are isoelectronic with the noble gases in front. So fluorine, for example, by gaining 1 electron, now has 10 electrons, which what neon does has 10 electrons. So it's isoelectronic with neon. Magnesium, when it loses 2 electrons, you're going to lose 2 electrons because it is in group 2. Okay, and it's going to lose those 2 valence electrons and now has 10 valence electrons, whereas before it started as 12 and losing 2 now has 10. So it is isoelectronic with neon, just like fluorine is isoelectronic with neon. Fluoride, P minus 3, which is now phosphide. I'm going to start using the names. Phosphide, which is the anion of phosphorus. By picking up 3 electrons, it is now isoelectronic with the noble gas in front of it. So one way to look at this, it may help you out, is for the nonmetals, the A nonmetals, when they lose electrons, they become isoelectronic with the noble gas behind it. And so sodium, when it loses 1 electron, is isoelectronic with neon. That's the noble gas behind it. Potassium, for example, is number 19, has 1 valence electron. When it loses that 1 valence electron, now it has 18 electrons, which is isoelectronic with argon. Okay. The nonmetals, when they become anions, are isoelectronic with the noble gas in front of it. So fluorine, notice when it becomes fluoride, notice the name there, okay? Fluorine, which is the element, when it becomes fluoride, which is the anion, picked up 1 electron, is isoelectronic with neon. Bromine, for example, bromine becomes bromide, is now isoelectronic with krypton, KR, the noble gas in front of it. So isoelectronic, I overemphasize, just means we have the same number of electrons. Does not mean it becomes the noble gas. It shares the number of electrons. So if we look at this table here, we've got calcium ion. Okay, here's the key. You got to look at it. It's not the element, and we know it's the ion, the cation, because they got a +2 charge. So we can write the electron configuration for calcium +2, the cation, and oxygen, which now is oxide, okay? And Cl negative now is chloride, okay? And the calcium ion is isoelectronic with argon. That's the noble gas behind it. The oxygen now becomes oxide, is isoelectronic with neon in front of it. The chlorine becomes chloride, and it's isoelectronic with argon, okay? Now, I can't overemphasize the naming here. This now is oxide. It's not oxygen, it's oxide. This one here is chloride, not chlorine. Okay. In the metals, we just call them, they don't change the name. It's just, this would be, if I needed to name this would be just say calcium ion. That's it. So the metals, there's no name change. So you can see here that the calcium ion and the chloride ion are isoelectronic with argon. They share the same number of electrons, whereas the oxide and the aluminum are isoelectronic with neon. Okay? They are not neon or argon, they are isoelectronic. They share the same number of electrons. Now, with respect to this kind of a table where we're given two elements, selenium and aluminum, and then they're giving us a specific isotope. In this case, it's selenium 78. Okay, which is element number 34. Which, if you think about it, you got to find it first. You got to find where it's at in the periodic table, number SE, which is number 34. The most common isotope for number 34 is actually selenium 79, but we're talking about selenium 78. And then we got aluminum. Aluminum is number 13, and the most common isotope of aluminum is aluminum isotope. Is aluminum 27, excuse me, which is what we're working with here. Okay. So the protons for selenium, obviously, is 34 all the way across, regardless if we're working with the element or the ion, in this case, the anion. Where they differ, obviously, is the number of electrons. The element has 34 electrons. It has 34 protons, 34 electrons. Okay. Se is in group 6. It is a nonmetal. So it will pick up 2 electrons, just like sulfur and oxygen. It will pick up 2 electrons. Those 3 share, they're in the same element. And so they will have a -2 charge. All right, so they have 36 electrons. This will have 36 electrons. Now, the number of neutrons, regardless if it's the element or the anion, is the same at 44. Okay? 44, that is the 34 plus the 44 gives me 78, the mass number. Aluminum is in group 3, and it's a nonmetal, so it's going to lose 3 electrons. So it has 13 protons, starts off with 13 electrons as the element, but when it becomes the cation, it loses 3 electrons, those 3 valence electrons. So now it has a 10 electrons. And the neutrons is simply the 13, the 27 minus 13 gives 14. Okay. All right. Well, be familiar with these kind of tables. You might find those, down the road someplace. So let me, that ends chapter 5. And any questions about that? Chapter 5. So if you do have a question, shoot me an email. I'll get to it as soon as I can. Now, remember, use the Canvas email. I do go periodically, and I do check my EDU email, but not very often. So if you send me an email through that, my EDU, I may not be able to get back to you as soon as I can. Okay, the periodic table. And this is a relatively short table. Okay, but it basically is some information concerning the periodic table and some trends in the periodic table. Okay. Now, the table itself is pretty old. Back in 1869, there's that crazy looking scientist here on the far right. The name is Dmitry Mendeleev. Dmitry Mendeleev was a Russian scientist, and based purely on observation, but keep in mind, it's 1869. Fancy scientific equipment like we have today was not available, and a lot of theory and a lot of ideas of how matter was made up of was based on observation. So based on his observation of the activity of different chemicals during his time, what he ended up doing was arranging the elements in the table of increasing mass. He's using the increasing mass of the elements. And what he did then was actually put elements with similar properties in the same column. Now, he figured there's something about them that they react very similar. Down the road, when we start learning about the electrons, we start knowing that, hey, they're in the same column because they share the same number of valence electrons. Therefore, they have a similar, and they share the properties, the chemical properties, because of the same number of valence electrons. But in his particular initial table, it left a lot of holes, and that initiated scientists to go look for these elements. It predicted certain elements to be there, and sure enough, a lot of new elements were discovered because of Dimitri's original periodic table. Another scientist by Moseley, I believe we pronounce that. His periodic table. By this time, we started getting more of them, discovering more of the elements. He put them in increasing atomic number. Okay, and also he put them in the same group. So he arranged his tables like Dimitri did. They're in the same column because of similar properties. So we have what's called the periodic law. Elements in the same column have similar properties. We know that that's the case now because of the same number of valence electrons. Okay. Now, if you look at the periodic table, we always show the bottom elements. What these down here at the bottom. Let me change the color a little bit. Down here, they get pulled out of the periodic table, and they generally belong because this is number 58. So 58 belongs starting right there, and then 90 goes after 89. So that's where they belong. If we were to do that, the periodic table would be stretched out. Okay. And so this next slide represents a periodic table stretched out, otherwise that long periodic table. You can see in the bottom left corner, this is how the modern periodic table is presented. And the green here, they have their own name. Those elements are essentially pulled out, and then the rest of them is shrunk in so we can visualize the elements. Also, you might find some periodic tables out there that do not use Roman numerals. They're beginning to use numbers like 1 through 18. That's the proposal of getting rid of the Roman numerals. I like the Roman numerals simply because it tells you how many valence electrons you have in the outermost shell. This doesn't. The numbers do not. So at a glance, Roman numerals do have some advantage. Okay. Anyway, there's other periodic tables that have been proposed. This one here is a circular periodic table. Yeah, you look at it as well. It does offer some advantages, but it's kind of difficult to really read and really look at. Another one is one that looks like this. In fact, this one actually predicts what are called the superactinides. There's a whole section here that when they eventually, and that would be right here, they're not full yet, but when we get into elements 119 and forward, and we start making these new elements, this is where it's predicted to be. Okay, so there are a variety of different presentations of the elements, but we tend to stick with the standard at this point until everybody decides which one they want to use. And here we have the modern periodic table, which represents here by different color the block, and that is the element S block. And remember, when we're doing the electron configuration, I said think of the first two group 1A and group 2 as the S elements. We call that the S block, and then we've got the D block and the P blocks and the F block, and those represent the orbits of the respective elements here. All right, so we know now, if I didn't mention it, but the horizontal row is called a period / energy level, okay? Because there's 7 periods that represent the 7 energy levels for the electron. The vertical columns are a group. And so we got group 1A all the way to 8A. And they're in that group because they exhibit similar properties, chemical properties, okay? And the ones with the Roman numeral A, 1A to 8A, those are called the main group elements. And then the ones in the inside that have the B lettering are what we call the transition metals. Okay, transition metals. So here's in yellow and crossed, which also represents the shells or energy levels. And then the groups denoted by the letter A are the same group. Now, the transition metals, as I just mentioned earlier, are the B, which are these guys in here. Whoa. I don't know what happened there. Yeah. Those are the transition metals. And then these are called the inner transition metals. We'll have, some of these have their own specific name. We're going to get to those here in a bit. Okay. Now, group 1A, they have their own special name. They're called the alkali metals. And now, with the exception of hydrogen, because obviously hydrogen is not a metal, it's a gas, okay, and it's a non-metal. But below that, lithium down, group 1A, they're called alkali metals. Group 2A, starting with beryllium down, are alkaline earth metals. Okay, the ones in group 7, starting with fluorine, and you got chlorine and bromine. Those have their own little name. They're called halogens. You may be familiar with these. Some of you may have light bulbs, halogen light bulbs on your vehicle. Okay. And then the final column on the far right, the group 8A, those are the noble gases because they have their octet full, with the exception of helium, which has their duet full. That's a duet group. They only got 2 electrons. Okay. So group 1A, alkaline metals, group 2A, alkaline earth metals. The halogens are group 7, and the noble gases are group 8A. Okay. We have the transition metals. Those are the ones in green. The B transition metals. Now, we can't predict their behavior, especially with respect to the charge. Unlike group 1A and group 2A metals that we know they're going to have a +1 and +2 charges, these transition metals can have a variable charge. Copper, for example, I mentioned before, can have a +1 or a +2 charge. Copper is number 29. Iron, number 26, can be a +2 or a +3. Okay, unpredictable, so we can't do a prediction there. And how many electrons they lose, it depends on the reaction and the conditions of the reaction. So those are called inner transition metals. These lower ones that we pulled out, they have their own little name. They're inner transition metals, but we have the gray, which are called the lanthanide series. Okay. The general name for both of these are called inner transition metals. And then the top gray color, I think it's gray, are called the lanthanide series. And they're also called the rare earth metals. Very expensive, used quite a bit in electronics for multiple things. And then the actinide series, basically, they're all radioactive elements. Okay. In fact, from element 93 up, 93 forward up to 118, they're all man-made, all radioactive, and they're made in what we call particle accelerators. We're taking particles and smashing them together to make new elements. Okay, you might get questions like this where it says, all right, an alkaline metal in the 3rd period. Well, you got to recognize what an alkali metal is, and obviously you know what the 3rd period is. So if we do that, alkali metals, those are the guys in group 1A. So sodium would represent the alkali metal in the 3rd period. Okay, and halogen in the 2nd period. Well, halogens are the group 7, and the 2nd period, that would be fluorine. And then a noble gas in the 4th period. Noble gas would be the last column. And then we go 4 periods down. That would be good old Kr, krypton. Okay, noble gas, krypton. Refresh your memory with respect to the metals and the non-metals and the metalloids. This is a slide that we did a while back. I will show it again for you. Okay. Now, with respect to the atomic size, I kind of introduced this a little bit in the beginning with respect to the atomic size and the radius, because I said we have energy levels, and I may have asked the question, who would you predict to be bigger in size with respect to, let me pull one up here. Let's say with respect to lithium versus potassium. Okay. Who would you predict to be bigger in size and radius? Who would have the larger radius? Potassium. Let me change the color. Lithium or potassium? Who would like to make that prediction? Who will be bigger in size? In radius?
Is it potassium?
Exactly. Be potassium, because potassium, its outermost, well, they both, first of all, what do they share? They're both in group 1A, okay? So they share being in the same group, which means there's one valence electron. Okay. All right. So further on, so the one valence electron for lithium is in the third energy level, whereas the one valence electron for potassium, it's in the fourth energy level, which means it's bigger. So the trend that you can deduce already from the periodic table is that when you go down the periodic table, guess what? The element gets bigger. The radius of that element gets bigger. It just gets bigger in size. All right. So where am I? So it increases down a group or a column. All right. Now, here's the troubling part that people may not get sometimes. Okay, let's go back to the periodic table. Let's see what you can predict. Let's compare. Okay, lithium with fluorine. Okay, now, can we predict, or what would your intuition tell you who is bigger in size? Lithium number 3 element or fluorine number 9 element? Now, no,
Fluorine.
fluorine will be bigger. Okay, that's your prediction. All right. Anybody else would disagree or agree?
I would agree.
Okay, got 2 agrees. Okay, minus 50 points. Just kidding. Now, think to look at this. This is good. You're analyzing this. Okay, you looked at it and said, fluorine is bigger. I would expect for it to be bigger. Okay, and it's a good observation. You can do that. It's not a problem with that. But I'm going to throw a little bit of curve. We understand that going down the periodic table, it gets bigger. Obviously, we're getting a bigger onion, if you will, bigger diameter. But going across, we're in the same energy level. Both lithium and fluorine are in the same energy level. So we're not increasing the energy level. So we're still within energy level number 2. So what differs between lithium and fluorine, guess what, is the number of protons, right? Because lithium has 3 protons, whereas fluorine has 9. So there's 6 more protons that fluorine has. More so than that is that lithium has 3 electrons and fluorine now has 9 electrons. Okay. And so keep in mind the positive protons and the negative electrons, there's a force there. I got a positive and negative attraction. This is where you get opposites attract, literally, they attract. Fluorine, because it has more protons, has more atomic force, if you will, to pull the electrons in closer to itself than lithium. The result is because fluorine has more protons, it's going to pull those electrons to itself even tighter than lithium. The result being that the radius of fluorine is smaller. Okay. And that's true going across the periodic table. That going across the periodic table, because we increase the number of protons and the electrons, we're adding more nuclear attraction, if you will, more force to pull those electrons into itself even tighter. It's like adding more magnets here. I got in lithium, I got 3 magnets. In fluorine, I got 9 magnets, and I put them, let them all attach to each other. Well, the 9 have a lot more force, total force of pulling everything in than the 3. Okay, so the train is going across the periodic table. The radius decreases because we are increasing the attractive forces of the proton and the electrons. And that's the key thing, because you could be asked a question, what's the trend across the table, across the periodic table, and be told, well, don't just regurgitate the trend. Why is it? Explain your trend, and there's the reason. As positive charges increases, the electrons are pulled closer. So the atom actually gets smaller in diameter. Okay. We can use the snowman as a kind of a guide to help you. So on the upright position, that's going down the periodic table. You can see that going down the periodic table simply because we have increasing the size of the element into the different energy levels, the radius gets bigger. But within the same energy level, going from left to right, just take that snowman and drop him. You can see the circles represent the radius. They're going from left to right. The radius of the atoms gets decreased in size. Okay, does that hopefully make sense there for you guys? And this is kind of a description. Now notice the one thing we learned, the one thing about science is that, there's nothing ever 100%. Trust me, if anybody tells you, it's 100% real or correct, no. There's not, even our measurements, we talk about our measurements, we never can get anything 100%. There's always some room for error. But the general trend as you go down the periodic table, that yes, even the columns, they get bigger, right? And you go across from left to right, the general trend is they get smaller. Okay. And yes, they might hop around a little bit, maybe not as drastic in size and diameter, but the general trend from left to right gets smaller. And these represent the respective diameters of the elements. So the bottom right corner is pretty small. You can look at helium. Helium is pretty tiny little thing, relative, size-wise. Okay. So here are the questions you might be asked is, okay, which is larger? Okay, oxygen, selenium, or beryllium? Well, what we got to do is we need to find them on the periodic table. And we look at where they are relative to each other. And we can see, guess what? All these 3 elements are in the same period, same group, I should say. Not period, same group. So they share the same number of valence electrons. They differ in that the valence electrons of Te are in a different energy level. So obviously going down, the radius gets larger. So Te would be larger, okay? Now with respect to magnesium, silicon, and sulfur, well, we're gonna first identify them on the periodic table and find out where they're at. And when we do that, you can see I got them highlighted here. They're going across there in the same period. Okay, magnesium period number 3, energy level number 3. And now, so being in the same energy level, we can't use the same thought process as we did for the first one. So we got to look at something else, and we find that going from magnesium to sulfur, sulfur has more electrons and more protons and more electronic force. So Magnesium would be bigger. Sulfur would be smaller in size. Okay, the size. Now, which if you think about this now, if you notice the trend as you go across the periodic table, sulfur is a non-metal. Okay, it's also smaller in diameter, has more protons. So it's going to want to hold on to their electrons much stronger than magnesium. Okay, and we'll learn here later on, there is a property we can measure for that. Being a non-metal, that's why they want to gain electrons. They're not going to give up those electrons very readily as compared to magnesium. So sulfur has more protons, more electrons. That force to remove an electron is going to be tougher than it is with magnesium. Okay. All right. And the same is true if you look at the trend, if they're in the same group, going down the periodic table. I mean, if we look at this group here, think about this for a while. What is it they all have in common? Well, they got 6 valence electrons. You're in the same group, 6 valence electrons. Well, the difference that oxygen has it in group period 2. Okay, selenium is 4 and 5 down respectively. So beryllium, its 6 electrons are like in the 5th, let me make sure, in the 5th energy level. They're much further away from the nucleus. And think for a moment, if your electrons are further away from you, you would expect that that interaction with the nucleus would be a lot weaker than if the electrons were, say, maybe the 2nd energy level. Okay. So the further away the electrons are from the nucleus, the less interaction they have with it, the weaker the interaction with the nucleus. So those electrons may be easily removed compared to the ones that are closer in to the nucleus. Keep that concept in mind. Okay. All right. So there is a video on atomic size, so you may want to take a look at it, read about it, and listen to it. You know, Dr. Kim does a very good job. Okay. Do see that. Now, we're still in the periodic table. Okay. Now there's 2 forces we're going to talk about. One is called ionization energy, and the other one is called electronegativity. What tends to happen is to get the 2 mixed up. Okay. Wholly different properties. Ionization energy is when you take a neutral atom, you take an element that has equal number of protons and equal number of electrons, and then you try to remove an electron, okay, with the X amount of energy. And so that ionization energy is a measure of the amount of energy necessary to remove an electron from a neutral atom, okay? And so from what we've been learning so far, you can probably make some predictions. We said that metals lose electrons more readily than nonmetals. Okay. Also, we see the trend that when we go across the periodic table, then nonmetals pick up more protons and more electrons. So the force that holds those electrons is much greater than those that do not have as many protons and electrons to hold on to them, right? So we can start hopefully seeing a little trend here. We can predict that when with respect to metals and nonmetals, that nonmetals will have a lower ionization energy than, let me repeat that. Metals will have a lower ionization energy than nonmetals. Why? Because metals have a tendency to readily give up their electrons compared to nonmetals that have a tendency to want to hold on to their electrons and gain electrons. So they're holding on to electrons much tighter. So the amount of energy required to pull one out will be much greater. Okay. All right. So as the ionization energy increases as we go up a group. okay? Going up the group, meaning that as we're in a group, let's pull up the periodic table. And let's simply just compare very generically two elements. This one and this one, 87 francium, okay? Now, what these two share is that they both have the same number of valence electrons. They both have one valence electron in the valence shell, the outermost shell. Lithium has its valence electron in the second energy level, compared to number 87 that has its energy valence electron in the energy level number 7, the last one. And so you can see that the interaction of holding on to that electron, attracting to it, the guy that's further away is going to have less interaction with the nucleus than the electron that's closer to the nucleus. And so lithium is going to want to hold on to its valence electron much greater than number 87, simply because in number 87, its valence electron is further away, okay, further away from the nucleus. And that is what it's telling you here, that so if we go up the periodic table, the ionization energy increases. It becomes greater and harder to remove an electron from one of these elements. Okay, simply because that electron is now closer to the nucleus, and it's holding on as the radius gets smaller. That electron is being held on strongly to the nucleus. Think about this. If I get two magnets, okay, and I keep them separated and don't let them come together. Obviously, if I just let those two magnets touch each other, they're attached to each other, right? No question there, right? But let's hold on to them and just bring them real close together. You can feel that force, but don't let them touch. Just keep them apart. You can feel the force that they're trying to pull together, right? But if I take that same magnet and I move it away a little bit, there's still a force there, but it's very small. Okay, it's very small. And that magnet that I have out here in one hand, I can easily remove it, compared to the magnet that's real close together. It's going to be a little bit tougher to pull away. Okay, and that's what they're telling you in the trend here, that down the periodic table, it takes less energy to remove an electron, simply because that electron is not interacting with the nucleus as strongly as the other ones that are smaller in diameter. Now, as we go from left to right, ionization energy increases, okay? It gets stronger. It takes more energy to remove electrons, because here we go again. On the far left, we have the metals. They want to give up their electrons a lot more readily than compared to the elements on the right, which are nonmetals. They want to hold on to the electrons, okay? And they want to hold on to electrons again, because as we go across the periodic table, we're picking up on the number of protons and the number of electrons. So that force gets stronger. That's why the radius shrunk. That force is stronger, and they're holding on to their electrons much tighter than the elements on the left, okay? And so nonmetals, they want to gain electrons. They don't want to lose them. So what electrons they have is going to take quite a bit of energy just to remove one. So that ionization, here's a reaction, a reaction that is occurring for the process. Let me highlight this. And so we're taking the neutral element and we hit it with energy. And the point of that is to remove an electron, which is right here on the right of the chemical reaction. Moving an electron gives us a positive charge. Okay. So if you think about this, if this was a non-metal, non-metals want to gain electrons. So yes, they can become temporarily a positive charge, but it can take a lot of energy for that to happen. Okay. So the result is this. You get a graph that looks like this. Okay, let's quickly analyze this graph. What we have here, color a little bit. We have on this axis units of energy. Not to be worried, concerned about the units or electrovolts, but just energy units. And then we go on the x-axis, we have atomic number, okay, of the element. So we look at the first element, we measure the amount of energy it takes for it to become ionized. And the very first element is right here, hydrogen, okay? And hydrogen gives you X amount of energy for it to remove an electron, which is probably what, about maybe 13.5 units of energy, ballpark, right? We go to the periodic table and we get helium. Wow. Look at the trend, how the big jump. It went from about 13.5 units of energy, almost to 25 units of energy on the periodic table. Because remember, as you go from left to right, ionization gets higher in energy, okay? Because those electrons are being held down much closer. We flip around the periodic table, we go to lithium. Lithium begins right there. And therefore, it's a metal. Its ionization energy is a little bit greater than 5. So as we go across the periodic table, it hops around, but the general trend, it goes up, okay? Oh, time. Oh, my goodness. Sorry about that. Hey, I appreciate it. I get a little carried away here. Okay, so we're almost done with this chapter. I will continue it on Thursday. And I'll start here where we at chapter 6, slide 22. All right. You know what I forgot to do? Did I start the recording? No, I did. I stopped.